I have good news for those of you who want to see me this week. I now have a reclining chair in my office. And I'll have a plentiful supply of paper towels for tears. Actually, I have to say, I underestimated the performance. You did much better than I thought as a whole class. But I will send out an announcement about when I can meet with you this week to discuss your performance. This time I'm going to look at people who performed below a certain cutoff. And you're going to have to come in if you're below that cutoff. So I will send an announcement. I had both the 120 and 20 exams in the same week, so I have to deal with those folks as well. And once I sort things out, I'll let you know. But don't worry, I haven't forgotten. And the solutions will go up soon. We had a couple of people who were taking it later because of out-of-town trips and so on. And I was moving over the weekend, so that's why there's a delay. Any questions? Yeah. No, it's all gone. I vacated the apartment, it's all gone. But I do have a 19-inch CRT monitor if you're interested. 1998 vintage. Works perfectly fine. Apparently architecture students love it. Love CRTs because somehow they don't like the LCD monitors. I don't know why. But, huh? Probably, yeah. All right. Now, a lot of you were not here in the lecture before the exam. So I'm going to review some of that stuff. We have now shifted into a very important phase of the class. This is basically the bread and butter of what you're going to be doing in signal processing later on. And we're about to build a very important bridge between the time domain and the frequency domain that I told you at the start of the semester we'll be hopping between. We've already been doing quite a bit of that when we've studied frequency responses and impulse responses. But now we're going to formalize all this process. So the way I'm going to do this is through the following roadmap. The signals that we study are, broadly speaking, in one of four categories. They're either discrete time or continuous time. And they're either periodic or aperiodic or non-periodic. It turns out that what we say in the bottom row for aperiodic signals also covers periodic signals. But the entry into this whole Fourier transform and Fourier series discussion is much more easily done for the periodic case, and that's why we start from there. So this is where, I'm going to start off with discrete time periodic signals, and we're going to describe the discrete Fourier series. There's a cousin of this called the discrete Fourier transform. And some of you may have heard the terminology fast Fourier transform. That's essentially a way of decomposing discrete time periodic signals into a linear combination of sinusoids or complex exponentials. That's what this whole discussion is about. Then we'll move to the continuous time story. For that, we simply call it Fourier series. That's what it's been historically called. And that's what we're going to do. So we start from here, move to that block. Then we get to discrete time aperiodic signals. And that's where we discuss the discrete time Fourier transform. Or the DTFT. And then from there, we move to the CTFT, continuous time Fourier transform. So this is DTFT. That's our roadmap for the rest of the semester. Okay? Now, what is this all about? Well, let's start with the simplest case, which is discrete time, periodic signals. Here's an example of that. 1, 2, 1, 2. 1, 2, 1, 2. Continues indefinitely in either direction, and there's your signal. Okay? One way to decompose a signal you've already seen. You write the signal as a linear combination. Let's write xk. xk of shifted impulses. Any discrete time signal you can take, and you can write it as a linear combination of shifted impulses. Now imagine we're dealing only with periodic signals of period 2, for example. Then you don't need all these shifted versions of it. You can look at impulse trains, 2 impulse trains. Periodic with period 2. I'll call this phi 0 of n. Okay? So this is, when you look at just one period, all you see is a 1 and a 0. And then I construct another one where I shift things a bit. So I have 0, 1, 2, a 1, a 0, a 1 here, a 0 here, a 1 there, and so on. I call this phi 1 of n. Can you write this signal in terms of a linear combination of these two? How do you do that? X of n is equal to? Phi 0 n times 1, which is x of 0, plus x of 1 times phi 1n. You agree? I take a linear combination of these 2 impulse trains. I scale the first one by 1, which is x0. And I scale the second one by x of 1. And I combine these, and I get my signal. If I want to do away with all the n dependence, I can write x is equal to x0 phi 0 plus x1 phi 1. Or, if you don't like that, as if I'm looking at vectors. And you can, in a sense, look at these as vectors, because all the action that takes place for a periodic signal is within one period. All the information about the signal is contained within that one period. So you take the signal x, and so here's my signal x, 1, 2, 1, 2. This is my x of n, okay? 0, 1, 2, 3, it repeats. I take one period. Here's my one period. And I stack the values in a vector. Two-dimensional vector. You agree? 1, 2. I stack it up as a vector. All the other periods are identical. So I've captured all the necessary information about this signal. And I can do the same thing with phi 0 and phi 1. So similarly, phi 0 would be, do the same with phi 0. Do the same with phi 0 n and phi 1 n. So phi 0 can be encapsulated with the vector 1, 0, and phi 1 is 0, 1. And all we're asking here is to decompose x as a linear combination of phi 0 and phi 1. So it's as if you're sitting in two-dimensional space. You have one vector, which is phi 0, 1, 0. And you have another vector, phi 1, which is 0, 1. And you've got your vector x, which is, I don't know if this is going to show up well. Tell me if you're at the back of the class and you can't see this. How does this show? Is that fine? Okay. And that's my vector x, which is 1, 2. And all we're asking is decompose x in terms of phi 0 and phi 1. And you say, well, that's easy. X is simply the first component of x, 1, times phi 0, plus the second component of x times phi 1. You with me so far? This is all high school stuff. Two-dimensional vectors. You can't get simpler than that. Well, one-dimensional, but that's not very interesting. So I'm starting with periodic signals of period 2, because they're the easiest to describe. You've got an encapsulation of the activity within one period inside a vector that's two-dimensional. And so you're living in two-dimensional space. And this two-dimensional space has two vectors that together can express any arbitrary vector in this two-dimensional space. And you know how to do that from your basic high school math. Now here's the nice thing about Fourier series. Fourier theory says x Fourier series it says not only can you express x in terms of these two particular signals, phi 0 and phi 1, but you can in fact express x as a linear combination of these signals. So here you have x is equal to, because we're living in two-dimensional space, you have as many of these terms in the summation as you have the period or the dimension of the vector x. But let's stay in 2 dimensions. Fourier series says you can decompose x in terms of these two functions. Now, this is pretty bizarre. It's not at all intuitive. And in fact, when Fourier, who was a physicist, proposed this, mathematicians laughed him off. There's a whole debate when he proposed this. Of course, when he proposed it, it was for continuous signals. The story is much simpler for discrete time signals. But essentially, this is not something that you would be able to guess. How the heck can you, first of all, this same signal, which is real valued, we're claiming is a linear combination of a bunch of complex valued functions. So phi k n, we're saying is e to the I k omega naught n, where omega naught is 2 pi over p. P is the period of the signal, period. And omega naught, I should say this is the fundamental period. And omega naught is the fundamental frequency. This is not intuitive, and that's why we're going to spend some time developing it. But essentially, in the case of two-dimensional periodic signals with period 2, these take on a nice form, and I can graph it on the two-dimensional plane. So if p is 2, what's omega naught? Pi. Right? So ck will be e to the I k pi n. Okay? Now let's plot this. How many of these do I need? How many k's? How many phis did I need? So how many c's do I need? 2. So let's plot C0 of n. What is that? If I plug in k equals 0, what do I get? 1. So I'm looking at this signal. All 1. 0, 1, 2, 3, minus 1, minus 2, and so on. What about C1? By the way, I didn't have to call these functions by different names. I could have called these phis as well. But it helps just to keep a comparison. What about C1? C0 of n, you said is e to the I 0 n, which is 1. What is C1 of n? E to the I pi n. E to the I pi n. How else can you write that? Huh? Negative 1 to the n. So when you plot this, you have an alternating sequence of 1s and minus 1s. 1, minus 1, 1, minus 1, and so on. So this is at 0, 1, 2, minus 1, and so on. Okay? So instead of these two functions being linearly combined to construct x, Fourier theory says you can combine these two and get your signal x. So now it's beginning. Now you can see the geometry a little bit better. So let's draw it out. Let's go back to our two-dimensional space. Instead of what I call the canonical vectors phi0 and phi1, which you're all familiar with, they're the two vectors that basically can be linearly combined to construct any vector in two-dimensional space. Now I'm looking at a set of slightly different vectors. What is C1 as a two-dimensional vector? Oh, I'm sorry, phi 0. Let's start with phi 0. C0. 1, 1. And C1, 1, negative 1. So instead of the red and the yellow vectors there, now I have C0 is 1, 1. And C1 is 1, negative 1. And I have my vector x, which is, what was it? 1, 2. Something like that. And what we're saying now is figure out how to combine these two vectors to get that vector. Are these two vectors perpendicular? Yes. They're as perpendicular as their cousins up there. And we use the word orthogonal for perpendicular. So C0 is orthogonal to C1. Here's the question now. How do you express x as a linear combination of these two? What's your proposal? No. I don't want numbers. I want methodology. So actually, I want you to talk to your neighbors and see what you remember from high school about how to decompose x as a linear combination of these two. Okay, who has a solution? Meatball. Oh, we don't have Math 54 as a prereq. So I don't want to hear the words, hear certain keywords that you learn in 54. Talk high school English. If you can explain it in 7th, 8th, 9th grade terms, I'm all ears. What do? I want the P word. What do you do with x with respect to the two vectors C0 and C1? You got 15 seconds. Project. You project what onto what? So to find x0 and x1, project. There's the key word. I want you to think throughout this whole discussion, I want you to think in terms of geometric concepts. We are now at a point where we're going to treat signals as vectors. That's the leap from what you know from high school to what we're about to learn in this class. We're going to start treating signals as vectors. So we're going to define things such as projection, angles between vectors, orthogonality or perpendicularity of vectors, and these kinds of geometric notions. So we project x onto C0 and C1, respectively. In fact, you did the same thing when we talked about phi0 and phi1. It's just that projecting x onto phi0 and phi1 can be done by eyeballing it. This one is not as straightforward. That's the only difference. You project x onto phi0. When you project, what number do you get? 1. You get the first component. And when you project x onto phi1, you get 2. So that you can do by just looking at it. In this case, you can't just do it by looking at it. So you've got to come up with a formal way. What does projection mean, Meatball? What does it mean to project x onto phi0? Right. And how do you do that? I want the DP terminology. Dot product. So you take the dot product, take the dot product, and here's where I have to do some weaning off. I'm going to wean you off this terminology. The term we're going to use instead of dot product from this point on is inner product. It's defined for a more general class of signals. Dot product you know as something that applies to real-valued vectors. We are no longer limited to real-valued vectors. For this particular case, this particular example, everything is real-valued. X is real-valued, C0 and C1 are real-valued. But you can easily see if I change the periodicity of the signal to 3, then C0 and C1 will no longer be real-valued. Well, this one will always be all ones. But these other ones, the C1 and C2, will no longer be real value. So one of the things we're going to do in this class, in fact, starting today, is to extend or generalize what you currently understand as the notion of dot product between real-valued vectors. And that notion is called inner product, and we'll define it. Don't worry about it yet. But let's talk about dot product for now. So you take the dot product of x with C0 and C1. So let's do that. How do you take the dot product? Again, you have different terminologies. X this is what most of you are used to. X dot product with C0. And how do you do that? What does this mean? What do you do? So remember, X is X0, X1. And C0 is C0, 0, and C0, 1, which is, in this case, this is, what is our signal? 1, 2. And this is 1, 1. So what's the dot product? How do you take the dot product of these two vectors? It's not a trick question. 1 times 1 plus 2 times 1. Now, just to not ruin the enthusiasm of meatball, you can also look at this as vector multiplication. 1, 2 times 1, 1. This is called the transpose of x. Transpose of x. And I apologize to those of you who've taken Math 54. Serves you right for being geeks and being ahead of the game. And this, of course, is C0. So this is X transpose C0. The corresponding notation for inner product is X C0. That's what we're going to get into our terminology. This is the inner product. But inner products are defined, this I write with hesitation. You'll never read something like that on top of an equality in a math class. Because inner products are defined slightly differently than this. There's a complex conjugation that occurs that we're not doing here. For real, when everything is real, the two definitions they collapse onto each other. They're the same. But when either x or C0 is different, then we got to change the definition. We'll do that. For now, just worry about the dot product. So you took the dot product of x with phi 0. Okay. But so when you take the dot product of x with phi 0 on the left side, you got to do the same thing on the right side. Yeah. So because we're dealing with periodic signals, I just look at one period. If I can decompose the signal within that one period, and I have a choice of how to pick that one period. It doesn't have to be 0, 1. It can be -1 or 0. Or it can be 1 and 2. But it doesn't matter. In this case, I've picked the intervals n equals 0 and n equals 1. So that's the interval I take. I can stack up the values of the signal into a vector form. So now it's as if I'm living in a two-dimensional space. If the signal is real valued, then it's a two-dimensional Cartesian, real valued Cartesian space that you know from high school. If the signal happens to be complex, then I'm living in a two-dimensional complex space, which is not as straightforward to draw. But this is all real because I want to push the geometric reasoning. So now I'm living in two-dimensional real valued space, and I'm going to appeal to what you know from high school about these vectors in two-dimensional space to arrive at a foundational expression for how to find these coefficients. The goal is to find these coefficients. And that's all I'm doing. Okay, so we're taking the dot product of x with phi 0. But if x is x1 phi 0 plus x2, C0, C1, yeah, x0, C0 plus x1, C1, and I'm taking the dot product of that with C0, then I've got to do the same thing on the right-hand side. So what happens when I take the dot product of this with C0? This is a number. This is a number. I don't know what those numbers are. But this is a vector and this is a vector, and I've got to take the dot product of this whole thing with C0. How does that work? Well, maybe this transpose notation is scaring you off. So let's wean you off gradually. X dot. What happens on the right-hand side? Constant. And then what? C0 dot C0 plus x1. C1 dot C0. What can you tell me about the second term? It's gone. Why? Because C1 is orthogonal to C0. So the orthogonality of these two functions, or these two vectors, is critical in this whole story. These two are perpendicular, or orthogonal. And that's why when I take the dot product of both sides with one of them, every term on the right-hand side drops out, except the one that contains that vector. So what am I left with? I have x C0 is equal to this number, C0 dot C0. What's the geometric interpretation of this? Magnitude squared. So can you tell me what x0 is? I don't want numbers. I just want everything in terms of x phi 0. X dot C0 divided by C0 dot C0, or magnitude C0 squared. And so if I ask you what's x1, what will you tell me? Are you going to go through all this? What are you going to say? X dot C1 over C1 dot C1. Now let's work out the numbers and see what we get. By the way, in the notation that Meatball likes, you'll have the coefficients as x transpose C0 over what? C0 transpose C1. C0. And in the notation that I want you to like, this is x inner product with C0 over C0 inner product with C0. And x1 is the same, except you replace 0 with 1. So it's x transpose C1 over C1 transpose C1. This, again, I write with hesitation because it's dangerous. I don't want you to think this is the definition of the inner product. But for real vectors, only for real vectors, oops, this has to be 1, C1, C1. Okay, what are the numbers? Can you work out the numbers and tell me? Are the lengths of the two vectors C0 and C1 different? So C0 is the same as C1 C1. And what is that? 2. So what's x0 now? So I've got a 2 in the denominator. For x1, I've got a 2 in the denominator. And what's x C0? Did we work out the numbers there? Well, I wrote it up, but we didn't write the numbers. What is the number there? 1 plus 2, 3. One, 2, times 1, 1, which is 3 over 2. Okay? And what's this guy? One minus 2, negative 1 over 2. So, yeah. the system of equations for two-dimensional case is straightforward. But the moment I go into a periodicity of 3 or higher, you're going to have a mess. So our decomposition says x0 is 3/2 c0 minus 1/2 c1. In other words, 1, 2 is equal to 3/2 1, 1 minus 1/2 1 minus 1. Does that work? 3/2 minus 1/2, that's 1. 3/2 plus 1/2, that's 2. What this means also is that when I look at x as a signal, it's the same as 3/2 v0n minus 1/2 c1n. So so I need 3/2 of this signal and minus 1/2 of this signal, and I combine them, and I get my answer. This is yeah. No. It just happens to be 2 in this case. It's the length of the vector, whatever it is. Yeah. Actually, for these exponentials, it turns out to be that. You're right. For these exponentials, it turns out to be no. Let's see. Will it work out to be that? E? Yeah, it does work out to be that. That's right. It works out to be the period for these complex exponentials. Now, there are also expansions of x in terms of sines and cosines. In fact, if those of you who take any physics class beyond the freshman year, probably in the first semester sophomore year, they teach when they talk about waves and vibrations, they talk about Fourier series, and they usually do it in terms of sines and cosines, not complex exponentials. But Fourier series expansion in terms of complex exponentials is much easier to do, much nicer to do, because it's much easier to multiply two exponentials than it is to multiply a cosine with a cosine or a cosine with a sine. And that's why throughout this class, even though the textbook treats, for the most part, Fourier series with sines and cosines, we'll deal with complex exponential expansions. So so essentially, this is what Fourier theory says. You either expand in terms of the impulses that you know, shifted impulses, 1, 0, 0, 1, or you expand in in a different setting where you have two different vectors that can linearly combine to produce any vector in the space. Bonsai! Have you had enough? Dumb question, sorry. I want to give you some assurance. If this is a rather abstract portion of the class, if it doesn't quite click with you the first time, don't worry. You're not alone. And we're going to repeat this over and over again. So eventually it'll sink in. But you'll probably have to watch the webcasts at least once, maybe a couple of times, to make sure you get it. And actually, I have to tell you, some of my best students over the years have told me that sometimes on some of the webcasts, they watch them up to 4 or 5 times. And these are some of my top students. So it takes some work. But if you get this notion, this geometric notion of treating signals, and if you become fluent with the notion of geometric reasoning and inner products and orthogonality, it has far-reaching ramifications. When you go into EE 126, or another type of continuous probability class, you can even treat random variables as vectors and discuss random variables that are orthogonal. And you can take inner products or dot products of random variables. And there's a whole area called estimation theory that involves this kind of geometric reasoning. So it's very important. Now, of course, we don't go into random signals in this class. But if you understand this notion of treating signals as vectors and thinking in terms of geometry, angles between vectors, orthogonality of vectors, and so on, then your subsequent classes will be much easier. Okay, so we have discussed the case, so we treated the case where the period is 2. And we said, okay, x of n can be thought of as x0 phi 0 of n plus x1 phi 1 of n. And he said, okay, in this case, where phi 0 is 1, 0, 1, 0, 1, 0, and phi 1 was 0, 1, 0, 1, 0, 1. And in this case, you had no trouble telling me that x0 is actually the value of the signal at 0, and x1 is x1. Now, this we're claiming is the more general set of formulas. So just to see that in this simple case, if you didn't want to eyeball it, you would get the same answer. Just look at what those equations say. So it says, take the dot product of x with phi 0 and divide it by the dot product of phi 0 with phi 0. What do you get? Within one period, my signal was 1, 2. Phi 0 was what? 1, 0. And in the denominator, you have 1, 0, dot product with 1, 0. What do you get? What do you get in the numerator? This 1 picks off the first entry. It always does that for this particular set of functions, the canonical signals. So you get 1. And remember, this is x at 0, and this is x at 1. So this one picks off x at 0. And in fact, let's write that first. X at 0 over, what's the length squared of phi 0? 1. So you get x0, which in this case happens to be 1. And you can do the same thing for capital X1, the coefficient that has to multiply phi1. Okay? Now, of course, we never do this when we have these kinds of functions because we know that this dot product always picks off the value of the first entry. The second one with this guy picks off the second entry. When I take the dot product of x with phi1, which is 0, 1, I pick off the value x1. Now things get more complicated when you have periods greater than 2. In terms of eyeballing things and drawing things. Okay? So let's say, what about p equals 3? Then I need 3 such functions, c0, c1, c2. And I need 3 coefficients, x0, x1, x2. And I have to say x is equal to x0, c0 plus x1, c1 plus x2, c2. If I'm dealing with complex exponentials, I'm looking at e to the I k. That's what Fourier series says, for Fourier series theory. Omega naught n. Omega naught is 2 pi over the period. So that's what I have. Let's write these out for the case where p is equal to 3. And you'll see why I start with 2 dimensions. What's C0? One. So when I want to write it as a vector, it'll be how many dimensions? 3. And what are the components? 1, 1, 1. Essentially, this is C0, 0, C0, 1, and C0, 2. Now, what about C1? Plug in k equals 1. You get e to the I, that's 1, 2 pi over 3, e to the I, 2 pi over 3 n. Right? Omega naught is, for p equals 3, omega naught is 2 pi over 3. Now stack this in a vector. So you've got to have C1 of 0, C1 of 1, and C1 of 2. What do you get? What's the first entry? 1. Second entry? E to the I, 2 pi over 3. And the last one? E to the I, 4 pi over 3. Already we've reached the stage where we can't draw these vectors anymore. And of course, C2 will be similarly defined. It's e to the I, 4 pi over 3n. And so C2 as a vector will be, what's the first entry? The first entry will always be 1 for these complex exponentials. And the second entry, e to the I, 4 pi over 3. And the third one? 8 pi over 3. Which is the same as? E to the I, 2 pi over 3. Because you can take out 6 pi over 3 from 8 pi over 3. Now, when you look at these 3 vectors, 1, 1, 1, 1 e to the I 2 pi over 3, e to the I 4 pi over 3, and then 1 e to the I 4 pi over 3, and e to the I 8 pi over 3, it's not at all obvious that you can represent even a real valued signal of period 3 as a linear combination of these. unless you've done the two-dimensional case and you see the methodology of how to do this. The only thing missing here now is the notion of projection. How do we project complex vectors onto one another? What's the dot product for complex valued vectors? The procedure will always be the same. xk, the equation that you get for the kth coefficient, will always be x ck over ck ck. This is common among all our common equation. And we'll derive this more substantively when I define the notion of an inner product or the generalization of dot product for you. But this is always going to be the equation. Yeah, question?
Do we know that C0, C1, and C2 are orthogonal?
No, not yet. Very good question. Do we know C0, C1, and C2 are orthogonal? Not yet. I haven't even defined the notion of inner product for you. How do you project one onto the other? Very good question. So I should actually make a note of that. We do not yet know. We don't yet know whether C0, C1, C2 are mutually orthogonal. And we know that this formula counts on them being orthogonal. So I'm cheating. The way we arrived at this formula in the previous case was by counting on the C0 and C1 being orthogonal. And that was easy to verify when C0 was 1, 1, and C1 was 1 minus 1. You just draw it and you see they're orthogonal. But what about complex valued vectors? Well, unless I define what it means to project one vector onto another, you won't know. So here's the next jump. Definition. There's no unique definition of inner products, by the way. But this is the definition we'll use. Definition we'll use for inner product of a vector f and a vector g, which is the generalization of the dot product. I'll do this by showing you an example. Suppose f is a vector 1i. Okay? Whatever definition we give to the inner product, when we take f and take its inner product with itself, I have to get what? Magnitude squared. Want, must have magnitude squared. Now, if a vector that I'm looking at is non-zero, does it make sense for its magnitude squared to be 0? No. What happens when you take the transpose of f with itself and apply the normal dot product? What do you get? You get 1 times 1 plus I times I, which is 1 minus 1, which is 0. Doesn't make any sense. So how do we fix it? Now, Meatball is taking Math 54 or has taken Math 54. What do we do with this, Meatball? you know? What do we do with inner products for complex valued vectors? Have they done that? Are you taking 54 now? You took it before? They didn't deal with complex vectors? Does anybody know? Complex conjugate of the second component. So F inner product with G, instead of it being F transpose G, you complex conjugate the second one. Doesn't have to be that way. In some books, they take F conjugate transpose times G. So they use F as the guinea pig. They put all the weight on its shoulders. They first conjugate it, transpose it, or they transpose it, conjugate it, and then they multiply it by G. But we use this definition, F transpose G conjugate. Now, if F and G are both real valued, what happens? G conjugate is equal to G. So if F and G are real valued, then our definition of the inner product becomes identical to what you know from before as the dot product. Because G is real valued. So when I take its complex conjugate, I get the same thing back. Okay? Now this thing has been, what's your name? Brian. This thing has been bugging Brian that we haven't shown that these vectors are orthogonal. So let's address that. So suppose I'm looking at phi k n, which is e to the I k 2 pi over p n. And I look at a different subscript, which is e to the I l 2 pi over p n. We can actually keep the 2 pi over p as omega naught, just to keep things a little less cluttered. E to the I l omega naught n. Okay? Now, with periodic signals, obviously they extend all the way from minus infinity to infinity. But we only have to deal with one period. And one period looks like just a vector, a p-dimensional vector. So when I look at phi k inner product with phi l, I'm looking at phi k 0, phi k 1, all the way to phi k, what? P minus 1. That's the vector ck transpose times what? CL 0 what? What's missing? Conjugate. CL1 all the way to C. Oh. Got to put it in red. Conjugate, don't forget. CL P minus 1. Well, what does that give you? CK, CL it looks like it's giving me CK0, CL conjugate 0, plus CK1, CL conjugate 1, CK P minus 1 times CL conjugate P minus 1. Can somebody please put me out of my misery and tell me how to write this in a summation? C, K, I. I is used in this class exclusively for the square root of negative 1. M times. Darn right, you're bad. Conjugate. M. And M goes from 0, P minus 1. So now let's plug it in. M equals 0 to P minus 1. CKM is e to the I. K, 2 omega naught. Yeah, thank you. Omega naught M. And what about CL conjugate? E to the negative I, L, omega naught M. So I have the summation to P minus 1, E to the I, K minus L, omega naught M. Are you all with me? Huh? What did he say for the past hour and a half? So this is the inner product. Whenever you have inside an integral or a sum an exponent an exponential, the exponent of which may or may not be 0, you've got to split it into two different cases. What happens if the exponent is 0? In other words, when k is equal to L. So I'm looking at CK, CK. What do you get? What's inside the sum? How many 1s am I adding? P minus 1 or P? P. Who was it who asked me if this is always going to be P? There you go. Okay? Now, what if k is not equal to L? Well, you'd hope, wouldn't you? This is where I have to give you a formula. M equals A to B. This is alpha. If alpha is not equal to 1, if alpha is not equal to 1, and that's the case when k is not equal to L. When k is not equal to L, whatever I'm taking to the mth power is not 1. If alpha is not equal to 1, this is going to be alpha b plus 1 minus alpha to the a over alpha minus 1. This is a finite sum you know probably from high school. And if you don't, I can derive it for you at the beginning of next lecture. Now, what is alpha in our case? Alpha for us is what? E to the I, k, minus L, omega naught. Okay, so now we're looking at CK, CL. So it's going to be the upper limit plus 1. E to the I, k minus L, omega naught, upper limit plus 1. P. You agree? Our B is P minus 1. So B plus 1 is P. Minus, what's the lower limit? 0. So alpha to the 0 is 1. I don't even care about the denominator. Don't care. I know it's going to be non-zero because alpha is not equal to 1. Right? Don't care. Now, can you tell me why this must be 1? Why is this quantity equal to 1? Omega naught p is 2 pi, right? The way they're defined. Omega naught p is 2 pi. So you're taking e to the I, some non-zero integer multiple of 2 pi. That's 1. Equal to 0. Brian's happy. And this is where I let you off. And I'll see you on Thursday.